very interesting work at the intersection of programming languages, formal methods, and machine learning theory, and has had some really exciting recent results on developing the theory of learning inductive invariance. So, Yotam, please.
Thank you. Thanks for having me. I'm really excited to be here. So I'm going to talk about joint work with Neil Immerman, Mulisa Gibb, Sharon Schramm, and James Wilcox about invariant inference, which is a set of techniques for proving the safety of transition systems, one of the fundamental problems in safety verification. So suppose, for example, you have a system over n propositional variables representing a number in binary, which starts from 0, and in each step incremented by some even number. So this defines the reachable states of the system. And we want to prove that no reachable state is a bad state. And here that would mean that it's the state where all the bits are 1. So this is the safety problem. And to prove safety, we want to find an inductive invariant, which is a set of states that includes all the initial states and excludes all the bad states and is closed under transitions of the system. So if you start from a state inside the invariant and make a transition, you also end up in a state inside the invariant. So for example, the property that not all bits are 1, of course, holds for this system, but it's not an inductive invariant because there is a transition from a state where not all bits are 1 to the state where all bits are 1. But we can strengthen this property to say that the least significant bit is not 1. And this is an inductive invariant. If you start from such a state, you also end up in such a state because that's how even numbers work. And once you have this inductive invariant, it over-approximates the set of reachable states and separates it from the set of bad states, establishing safety. So in invariant inference, we want to automatically find inductive invariants, thereby prove the safety of transition systems. And what I want to talk about today is our attempts at understanding the theory and the complexity of invariant inference algorithms by studying the connections and differences with exact concept learning and classification. So I'm going to set up query-based learning models for invariant inference and study the power of different queries. We're going to see that invariant inference is harder in general than concept learning, than classification, with interesting implications on the complexity of learning from examples, as it depends on the form of examples. But we're going to see that despite this hardness, the best complexity bounds we have for invariant inference algorithms actually originate from exact concept learning with some additional components to bridge these two worlds. Okay, so let's start by being specific about the setting. So we're interested in Boolean transition systems, Boolean programs over n propositional variables. And the problem is, given a transition system from a certain class, we want to find an inductive invariant that's from an expressive language, like a rich syntactic form of DNF formulas, disjunction of conjunctions, not merely conjunctions. So it's a rich syntactic class, but we restrict or assume the invariant size is bounded by some polynomial, because there is, if the only invariants are exponentially long, there's no hope of learning the invariant efficiently. So these are the kinds of invariants we want to find. And there's a decision problem. This is complete for the second level of the polynomial hierarchy. So it's anti-complete with access to a SAT solver. So there are many algorithms, existing algorithms, that try in practice to find inductive invariants. I want to focus on a very influential approach by Macmillan, that of interpolation-based invariant inference. So I'm going to show you the algorithm, and then we're going to ponder its complexity. So this is how it works. We start with the candidate invariant, that's just the initial states, and we verify that no such state can reach a bad state in k+1 steps of the system. So that's bounded model checking with a bound of k+1. Now, this is probably not closed under transitions of the system, so we need to consider all the states reachable in one step from our current candidate. And we know about these states that they can't reach a bad state in k steps of the system. Now, the idea of interpolation is to find a generalization of this fact, a larger set in which still all states cannot reach a bad state in k steps, and include all these states as our next candidate invariant. And we do that to achieve faster convergence. once we have this new candidate, we again do bounded model checking of k+1. We again look at the post image, try to generalize that by finding an interpolant, adding this to the candidate, and so on and so forth until we converge to an inductive invariant. If it so happens that at some point we have included a state that can reach a bad state in k+1 steps, then this is a failure of the algorithm and it needs to be restarted with a larger bound k. Okay, so this is the overall structure of the algorithm. Now the question is how to find these generalizations, how to find these interpolants. So here's one model-based approach that's inspired by a different algorithm by IC3PDR, and I'm going to demonstrate it on the example system we had before. So the way it works, it samples a state from the set of states reachable in one step from the current candidate. So for example, it could be this state. And now we write the conjunction that captures exactly that state. So clearly, every state that satisfies this conjunction cannot reach a bad state in k steps of the system. And now to generalize, we try to drop literals from the conjunction. So we try to drop this literal and see if the states that satisfy the remaining conjunction also can't reach a bad state in k steps of the system. And in this case, they can't. So we drop this literal. And we move on to checking the next literal. So we try to drop this literal and checking whether and check whether the states that satisfy this remaining conjunction cannot reach a bad state. And indeed they can't, so we drop also this literal. When we try to do the same for the least significant bit, we see that actually if we drop it, then there is a state that can reach a bad state in k steps for k greater or equal to 1. So we can't drop this literal, so we don't. And we do this for all literals. And in this case, we end up with the property that the least significant bit is 0. We add all these states to the invariant. In this case, this actually is already an inductive invariant. Otherwise, we need to sample more states and generalize by dropping literals and so forth. So overall, the algorithm computes an invariant in disjunctive normal form, where each disjunct is obtained from generalizing some counterexample to induction of the current candidate. And the generalization works by dropping literals as long as this bounded model checking still holds. Okay, so this is the algorithm. And I think it begs the question of why. Why is this what the algorithm is doing, and why do we expect this to work, or what's the complexity of this algorithm? So what's the deal with this bounded model checking? And this pattern of dropping literals, why does it make sense? Or maybe there are other things that make sense. So what I'm going to show is that this bounded model check actually does something remarkable that cannot be simulated by less than an exponential number of inductiveness checks. If you were to try to do inference without using such rich queries. And I'm going to show that this pattern of dropping literals can be understood as a manifestation of an algorithm from exact concept learning, from classification, and actually complexity results for this invariant inference algorithm can be obtained by translating complexity results from the concept learning algorithm. So all of this builds on the connections between invariant inference and exact concept learning. So let's talk about exact concept learning. So this should be familiar at this point. So we're trying to identify an unknown formula phi by asking a series of questions. For example, the learner can ask, is this formula psi1? And the teacher responds either yes or no plus counterexample. The learner then may ask, is it psi2? And the teacher responds. These are called equivalence queries. There are also membership queries where, for example, the learner chooses a state or evaluation, and the teacher responds whether this is a model of the unknown formula, it belongs to the concept or not. So these are membership queries. After a series of such queries, the algorithm needs to identify the unknown formula phi. And although I keep using the word teacher, it's not a teaching model. The word oracle is better here, because we're studying the complexity under a worst case assumption So the worst case of the possible examples that the teacher may return. Okay, so this is the model and it's great. Many algorithms and many results. Can we use these for invariant inference? So use the same approach to infer inductive invariance. So the problem is that we need to implement the algorithm, but we also need somehow to implement the teacher and answer these queries. But the teacher doesn't actually know, or we as an algorithm, we don't know the inductive invariant. All we know is the program. So it doesn't seem, so it seems that we need something else for invariant inference, or different learning models for invariant inference. So that's what I'm going to do now. So one thing the Oracle can do is, given a candidate invariant, return whether it's indeed an inductive invariant or that it is not, and return a counterexample. And here counterexamples are counterexamples to induction. That is, they are a transition from a state that satisfies the candidate the algorithm proposed to from a state that satisfies the candidate to a state that doesn't. And so the learner chooses a series of such candidates, and the Oracle returns counterexamples to induction. And after a series of such queries, the algorithm needs to find an inductive invariant. And in this model, the algorithm can't access the program or the transition relation, but through such inductiveness queries. And the complexity is the number of inductiveness queries it needs to perform, worst case amongst all possible counterexamples. And it makes sense because usually we don't have very useful notions of how the Oracle can choose counterexamples, and they usually come from a SAT solver. Okay, so this is the model, and it's essentially the ICE learning model of Gang et al. Now, when we try to look at the algorithm we had before and model it in this model, so we look at the places that access the program. These are the places. So this is an inductiveness query, but the bounded model check that happens in generalizations, this seems to be something else. So to capture this algorithm, we need to extend the model and introduce a new learning model for invariant inference, which we call the WholeQuery model. And in this model, the algorithm chooses a precondition alpha and a postcondition beta, sends them to the Oracle, and the Oracle responds whether the precondition guarantees the postcondition after one transition of the system. So if you start from a state that satisfies alpha and make a transition, whether you necessarily end up in a state that satisfies beta. And after a series of such queries, the algorithm needs to find an inductive invariant, and the complexity is the number of queries it needs to perform. And although this seems a very simple model, it actually can capture a very large of interesting existing invariant inference algorithms, including IC3 PDR. And when we look at the algorithm I showed you before and try to model it in this model, so this part is a whole query where the precondition and the postcondition are the same, the current candidate, and we can find a counterexample using a linear number of whole queries by essentially the self-reducibility of satisfiability. The point is that we can implement inductiveness queries in the WholeQuery model, and this query is this check is a whole query where crucially the precondition and postcondition are not the same. So we can model this algorithm in this model, at least when the bound for bounded model checking is 1, and we can very easily extend the model for any polynomially large bound in bounded model checking, but that's not the point I want to make now. The point I want to make is that this model, the WholeQuery model, is strictly stronger than the inductiveness query model. So there's a class of transition systems and invariants for which there exists an efficient algorithm in the WholeQuery model, but every algorithm that only uses inductiveness queries requires an exponential number of such queries. So there's a separation between these models. And the algorithm that actually achieves the upper bound is in fact a simple case of IC3 PDR, which proves that ICE can't model PDR and the extension by Vizeli et al. Is necessary. This upper bound is also achieved by the same algorithm I showed you with the bound of 1. And the part in the algorithm that can't be modeled using inductiveness queries is exactly this bounded model checking that happens in generalization. So this shows the importance of this check for the power of this algorithm. Now, I want to highlight the fact that actually this exponential lower bound is quite unusual in exact concept learning. And it attests to the inherent ambiguity of counterexamples to induction. So let's think for a moment, forget about invariant inference and think about classification. So thinking about classification and through a series of equivalence queries without membership queries. So we try to identify the unknown formula by proposing candidates and getting counterexamples. And classically, these counterexamples are labeled examples. They're either positive or negative, or we know if the example is positive or negative. But in invariant inference, what makes sense is counterexamples to induction, which are actually a pair of examples. One of them is negative, or the other is positive, and we don't know which is the case. And this ambiguity has an effect on the complexity. So if we try to look at identifying monotone DNF formulas, then classically the complexity is sub-exponential or even polynomial if you allow exponentially long queries. But the lower bound I show you is truly exponential. So this shows that there's a gap between learning from classical examples, labeled examples, and counterexamples to induction, which more generally shows that the convergence rate of counterexample guided inductive synthesis depends on the form of counterexamples. Okay, so this was about learning models and the power of different queries. Now I want to briefly talk about complexity bounds from exact classification algorithms and this pattern of dropping literals. So again, we're thinking about exact concept learning with equivalence and membership queries. And we really would like to use these algorithms and these complexity results. But we know that we have a problem that we don't know, the teacher doesn't know the invariant. And so that's why we set up different models for invariant inference. And the question is, can we translate from the exact learning model to the WholeQuery model? And the answer is no. We can show an exponential lower bound that shows aspiration and shows that it's impossible in the WholeQuery model to implement either equivalence queries or membership queries. But there are sufficient conditions that allow this transformation and allow us to obtain an invariant inference algorithm from an exact learning algorithm. And the reason this is interesting is because if we take a classical algorithm for learning DNF formulas, we take the queries and we implement them for invariant inference using an inductiveness check for equivalence and bounded model checking for membership, the result is the very same algorithm I showed you. And this is interesting because it means that we can translate complexity results from the learning algorithm to the invariant inference algorithm, provided that some extra conditions hold, because this transformation doesn't work in general. And these are conditions about reachability in the system, or really about the Hamming geometry of the reachability. So this is what we call the fence condition. And essentially it says that we're thinking about the state space of the system as vertices of the Boolean hypercube. And if this is the invariant, then this is the boundary of the invariance, the set of states of Hamming distance 1 from the invariant. And the fence condition requires that these states which are outside the invariant, they all can reach a bad state in k steps. So this is the fence condition. And if it holds, that is, if there exists an invariant that satisfies the fence condition and it has a syntactic form that matches results in concept learning with some restrictions. So if it's a short monotone DNF formula, it doesn't have negated variables, or if it's an almost monotone short DNF formula, it has at most a constant number of terms with negated variables, then we can prove that the invariant inference algorithm I showed you, or slightly different variants, can efficiently infer the invariant in a polynomial number of SAT codes. Okay, so overall, I talked about the connections and differences between invariant inference and exact concept learning. There are still many things about these relations and the complexity of invariant inference that we don't understand and would like to understand. But we do know some things about query-based learning models for invariant inference and the power of different queries. We know that invariant inference is harder in general than concept learning, with implications on learning from examples and learning from counterexamples versus classical examples, and that we can obtain complexity results for invariant inference from classification algorithms. Thank you.
Thank you, Yotam. There is a clarification question in the chat, which is, I think, about your theorem, the first theorem from your Popple 2020 paper. What is n here? Is it the number of state variables or a number of states?
Yeah, so n is the number of state variables.
Okay, great. I have a question about your modeling of PDR in the WholeQuery model. So you showed us the model for PDR1, right? Can you say a little bit about generalizing that to arbitrary PDR?
So yeah, so the WholeQuery model can model at least the basic. Okay, so there are many different variants of PDR, but at least a canonical PDR can be captured exactly in the WholeQuery model. It only uses checks of reachability of one step of the system. If you look into interpolation that uses bounded model checking with a larger bound, then we have an extension of the model that simply has an extended WholeQuery. So the learner chooses a precondition, a postcondition, and a bound that needs to be polynomial in the number of state variables, and everything else is the same. And the lower bound, the exponential lower bound that shows that equivalence queries and membership queries can't be implemented still holds.
I see. Okay, there's a question in the Q&A from Saleh El Mohammad. The question is, so roughly if we think of invariant generation as a CSP, constraint satisfaction problem, then what we have is just a classical relaxation algorithm?
So that's a deep question that I need to ponder, but in both cases, we're learning something exact, and also in exact concept learning and in invariant inference, we're finding an invariant that actually is an inductive invariant, not an approximation. Maybe we should talk about it more afterwards.
Great. I have one more question on your latter result, right? So you showed there how you can use exact concept learning algorithms to be able to do invariant inference with these side conditions, right, on the K-fence and so forth. Do you have results going the other direction? That is, you can do exact concept learning using the WholeQuery model?
That's an interesting topic that we haven't studied. Yeah.
Okay. Okay. I don't see any other questions, and so thank you once again, Yotam.
Thank you.